Hi, everyone. Thanks, Will, so much for that introduction. Today, today, Julie and I will both be talking about just one aspect of our highly collaborative research to fill data gaps with the ultimate goal of improving salt marsh restoration decision-making. Like Will alluded to, we are a double feature. So first you'll hear from me, and I'll be talking about mapping ditches across the Northeastern salt marshes. And then you'll hear from Julie about influences of ditches on salt marsh vulnerability in the Northeast. And then we'll jointly take questions at the end. I want to highlight that this is a highly collaborative research project. Julie and I have been working across 11 states with over 20 participants, 4 academic institutions, 3 federal agencies, 2 nonprofits, and our group is growing all the time. So please email us if you would like to be included in our roughly monthly groups. And the goal of our group is to effectively restore salt marshes and inform decision-making for salt marsh restoration. And through conversations with our partners, we've identified a need for improved understanding of where human modifications are affecting salt marshes in the Northeast and how human modifications are affecting the resiliency of salt marshes to drowning, which are under threat from rising sea level. And so today, I'm going to be talking about one major human modification to northeastern salt marshes, which are ditches. So ditches are these linear trenches that were dug into salt marshes to increase drainage of the salt marsh platform. So early Euro-American farmers dug these ditches to improve yield for salt hay, as you can see in the first image. And that salt hay was used to feed horses and cattle. Ditching greatly intensified in the early part of the 20th century for mosquito control, and the majority of this work was done by the Civilian Conservation Corps, or the CCC. Studies from the 1950s to today estimate that nearly all salt marshes in the Northeast have been ditched. And so Julie and I wanted to address this question: what are the effects of ditching on salt marsh vulnerability to drowning across the Northeast? So because ditches drain the marsh platform, they increase decomposition within the sediments. They also decrease flooding or inundation of the marshes and thereby decrease sediment input. We also know that ditches likely cause shifting vegetation communities, and this results in what we believe to be is reduced below ground biomass production. So taking all of this together, we expect that ditches will lower salt marsh elevation and make these systems more vulnerable to drowning under accelerated sea level rise. But first, we needed to determine ditch distributions across the Northeast. And so we did this by compiling linearly digitized ditch data for as many marshes as possible, basically trying to group as much data together as we could possibly find. But unfortunately for us, that data was only available for less than 5% of the greater than 3,500 square kilometers of salt marsh for the Northeast coast. So we set about hand digitizing the rest of the marsh polygons, literally digitizing each of those individual ditches that we could see in the aerial imagery. And we came up with what we believe to be as a fairly complete data set for the present. And so before we move forward, I want to make a note on hand digitizing. So as many of you may be familiar with, there are some obvious limitations to hand digitizing, not least of which is that it is extremely time consuming, and it can be difficult to determine whether or not you've actually digitized the object in question accurately. This is somewhat of a shameless plug to say that if you have also mapped ditches in salt marshes, sort of boots on the ground with RTK GPS, we'd love to work with you to compare our data sets to be able to better assess the accuracy of the data set that we've created. But in terms of precision, we knew with hand digitizing that it can be hard to know whether or not multiple people who are digitizing the same polygon are doing it the same way. So we paid a lot of attention to this, and we found that in Barnstable Marsh in Massachusetts, as shown in the image here, where we had 7 different overlapping hand digitized ditch layers, we found that the total ditch length only varied by about 13%. So we feel pretty good that all of these different data sets are comparable for the entire Northeast. And ultimately, Julie and I looked at every single polygon for the entire Northeast. So no matter what, at least 2 pairs of eyes were on every single salt marsh area in the Northeast. And the real benefit to hand digitizing is that it's super simple, and we think there's a lot of value in that. One of the other options besides hand digitizing is training an AI program to identify ditches and segment accordingly. So with this method, such as was performed by Karen Arney in her recent publication, you get areas of ditches, as you can see in this image here, rather than total lengths. And so obviously whether you want ditched area or ditch length all depends on the question that you're actually asking. So moving forward with the hand digitized ditch layer, for those of you who like fun statistics, the total length of ditches that we digitized was greater than the diameter of the Earth. Ultimately, we cared more about ditch density, which is the total sum of ditches within a single polygon divided by the marsh area. So we end up with the units of kilometers of ditches per kilometer squared of salt marsh. And so note that that area term within the calculation that we used, so we can get at salt marsh area a couple of different ways. And so the first way that we could estimate salt marsh area is we could just use the National Wetland Inventory polygons. The National Wetland Inventory polygons, or the NWI polygons, this is what we used as sort of the bounds, the footprint, when we were digitizing ditches. And the benefit of using NWI is that it's available for the entire Northeast. If you've ever used NWI, though, you know there are many issues. There are lots of areas that can be inaccurate. And the areas of the NWI polygons are not actually standardized in a really clear, obvious way. What would be better to use for salt marsh area is actually the USGS produced marsh units, which are based on elevation and tide range and are calculated as drainage areas or tide sheds. You can see sort of the difference between the NWI polygons in purple and then the black marsh units plotted on top. So they're smaller and perhaps more representative of kind of like a drainage area within the salt marsh. Unfortunately, marsh units are not available for the entirety of the Northeast coast yet. So another thing that we could do, which we have done, is create pixels of standard size that fill in the NWI polygons. And I've plotted those here as well. So those sort of polygons that are pixel sizes, we plotted at 30 meter, 165, 300, 1,650, and 3,000 meter resolution. And so this question that I have at the top of the slide, where does a salt marsh begin and end? How big is a salt marsh? Is obviously a very philosophical question, but how you answer it actually very much changes how we can interpret the data. And so we'll see that in 2 slides. But first, what does the ditch distribution look like across the Northeast? So I've plotted ditch density at the 300 meter raster resolution for salt marshes from Maine to Virginia. The white areas on the screen indicate no visible ditches, and the dark red areas are highly ditched pixels. As you can see, the ditch density is highest between Maryland and New Hampshire, with the lowest densities in Chesapeake and the Eastern Shore of Virginia. We have a zoomed in picture here of Massachusetts and Rhode Island on the right. So you can see just how dense these ditches tend to be in certain areas of the coast. But we do see large regions in the Northeast, especially around the Chesapeake and Eastern Shore of Virginia, where there's very little ditching. So you can see the contrast here in Chincoteague, where on the Maryland half of the bay, we see really high ditch densities, but in the southern portion on the Virginia side, we see very little ditching in those salt marshes. And so a lot of people are interested in this question of how much of the Northeast is actually ditched. So previous estimates are around 90 to 95% of the Northeast was ditched. But what does our data tell us? And before I show you that, I want to again impress upon everyone that the scale at which we measure the salt marsh area really matters when trying to answer this question. So again, this figure on the left is displaying the range of pixel resolutions over which we've calculated ditch density. And at the highest resolutions plotted in red, those 30-meter pixels, you can barely see those pixels on the screen. And so many of the marsh pixels for that 30-meter resolution will ultimately fall between the ditches being counted as unditched. At the lowest resolution or the highest pixel size, which I've plotted here in blue at 3,000 meters, the marsh pixels actually incorporate huge swaths of marsh. So maybe this is more appropriate, or maybe it's integrating over too large of an area. But unsurprisingly, the pixel resolution that we analyze actually affects the percent area ditched across the Northeast, as you can see on this plot. So the black dots show again the 30-meter, 165, 300, 1,650, and 3,000 meter resolution pixel data. And at the lowest resolutions, the highest pixel size, our percent area that is ditched in the Northeast increases. And so it's only at these maximum pixel sizes, around 3,000 meters, that we start to approximate what others have previously observed, that roughly 90 to 95% of salt marshes in the Northeast have been ditched. So what is the correct answer to how much of the Northeast is ditched? The answer is that there is no simple answer because it all depends on the resolution over which we're measuring ditches. And so ultimately, the resolution is dictated by the question being asked. So it's a little bit circular. For a quick and dirty statistic, I would go with the marsh units because they're determined based on, again, the tide shed. And the great thing is that we will be providing the polyline data to everybody. We think it should be released on Sciencebase in the next 2 weeks or so. And so you can actually use the data in your marsh of interest to assess questions about how to manage or restore your salt marshes. And so some quick concluding remarks just about the data set before Julie jumps into one way that you can use the data set. So we recognize that the data set has some weaknesses, but we think it could be really useful for those who want to know how ditched their salt marshes are, and for people who are interested in how ditches might ultimately affect salt marsh vulnerability or resilience in the face of sea level rise and other stressors. But when using our ditch data set, which again will hopefully be available in the next week or two, you have to remember that the scale you use for salt marsh area truly does matter. And so I'm going to stop sharing, and Julie is going to share her screen.
All right, doing a little quick switch here. As Erin alluded to, this is part 2 of our talk. So same people, same places, just slightly different things. So Erin gave a great introduction to our ditch data layer that we spent a lot of time kind of compiling. And then once we had this great data set available to us, we wanted to know what we wanted to do with it. So the first question that we wanted to ask was, how are these ditches affecting the vulnerability of marshes in the Northeast? So in order to do this, we utilize the UVVR vulnerability metric. And in case you're not familiar with it, UVVR is this unitless measurement of the ratio of unvegetated to vegetated marsh area. So this metric was developed based on Landsat imagery, and it's been shown to scale with the sediment budgets of microtidal marsh complexes in both the Atlantic and the Pacific coasts. And this is across differences in sea level, tidal range, elevation, vegetation, and other environmental stressors. So this means that it's pretty effective at assessing vulnerability to drowning across multiple systems. So under this metric, high values, so areas with more unvegetated area are more vulnerable, and lower values or areas with more vegetated area are more resilient to drowning. So the first thing we did was we brought in our ditch data set and we brought in the UVVR data set, and we did just a quick eyeball check of our data. And what we found was what seems some pretty ironclad evidence supporting the hypothesis that ditches are increasing marsh vulnerability, specifically in Chincoteague, Virginia, which you might remember being an example that Erin highlighted in the first part of this talk. So in this region, you can see this obvious trend of high ditching in the Northern Maryland section, coupled with very low density ditch site in the Southern Virginia portion. And you can see that this highly ditched region has a higher UVVR, being more vulnerable, and the less ditched region has a lower UVVR, making it less vulnerable. So this got us pretty excited about the prospect of actually quantifying this link between ditches and vulnerability. However, this excitement was pretty short-lived because when we took a look at the data across the entire region, we found there wasn't really a clear relationship between ditch density and UVVR. And that very minimal effect that we did find was slightly positive. So it was showing that these ditches were slightly beneficial to preventing these marshes from drowning, which was kind of counterintuitive to what we were expecting to find. So this caused us to do a little head scratching and think a little bit harder about how we were thinking about our data. And one of these questions that we asked ourselves was if we were looking at our data at the wrong spatial scale. So as Erin mentioned in her talk as well, spatial scale is very important when looking at your at ecological or physical questions. And this question is no exception. And so because we are looking at data across the entire Northeast, it is pretty likely that these patterns in UVVR are being influenced by large-scale drivers, and the effect of ditches is possibly being lost in this noise. So we looked at this hierarchy that was proposed by Yondo et al. In 2023. And we aim to subset our data on these higher order processes that are likely affecting marsh environmental factors as a whole.
Julie?
Yes.
Sorry, you dropped out for a second. Maybe if you could go back, maybe 30 seconds and
Oh, no worries, no worries.
start
Was I on this
there.
slide?
Yes, yeah.
Okay, okay. So basically what I was saying was that we wanted to, because we're looking at our data across the entire Northeast, there's likely higher order processes that are influencing UVVR or vulnerability that might be affecting UVVR on a higher scale than ditches. So ditches might be being lost in the noise of these other relationships. So we use this hierarchy of key drivers that affect marsh processes proposed by Yondo et al. To kind of subset our data based on this hierarchical kind of process. So since in the Northeast, we all lie in a similar temperature and precipitation ecoregion, we kind of set our sights on the next level down, which is labeled the coastal drivers, such as tides, wave energy, and river inputs. And we agreed with Yonda that this might be important drivers to account for in our data set because they can result in the creation of vastly different coastlines. And these vastly different coastlines are likely to be pretty influential on vegetation, which is what we are using for our vulnerability metric. So we combined the data sets on tides from the USGS Marsh Unit data set, river inputs from the Sparrow model, and wave data set also available by USGS. And once we did that, we plotted all of the marsh units based on these different factors and coded them with the different regions that they resided in. And we found that you do see some similarity of tidal factors based on regions, but also quite a bit of overlap. And this makes sense because coastlines can be pretty variable, and you can find multiple examples of these different geomorphic settings in the same region. And because of this, instead of just grouping our marsh units based on their geography to reduce the noise produced by these coastal processes, we decided to dig a little bit deeper and create typologies of these marsh units based on these geomorphic settings using cluster analysis. So cluster analysis creates cluster groups of data sets where the data is more similar to each other within the cluster than they are to points outside of the cluster. And this is what the results of this analysis looked like. And we resulted in creating more discrete groupings than if we were just to subset our data based on the different regions. So then based on these cluster groupings that represent the different geomorphic settings, we wanted to relate each of those clusters to whether that is affecting the UVVR and ditch relationship. But what we found was that there was still no clear relationship between UVVR and ditches, even when we subsetted them out by these cluster groupings, which was also, again, not what we were expecting. So again, we went back to the drawing board and we thought to ourselves, okay, if these ditches are not driving vulnerability, what possibly could be? So we turned our focus to the intersystem level to see what other factors might be influencing vulnerability to a greater degree than ditches. And this brings us back to Chincoteague, which is what we thought was this kind of gold star example of the effect of ditches on UVVR. But when we started to look at other potential influences, such as this example of relative sea level rise, and we found in this region that at the north that had the higher ditching and the high UVR also has a higher rate of relative sea level rise when compared to the southern section. So in this cases, ditches might have been more of a smokescreen hiding what could have been the real relationship. So based on this information, we decided to add more of these possible drivers to our model, and we added relative sea level rise, tidal restriction intensity, suspended sediment, and elevation data. And what we found was that even when we added these variables that we suspected were influencing marsh vulnerability at a greater rate than ditches, we still had very poor model fit. So it wasn't explaining much of the variability in UVVR. And we had an R2 of only about 0.06. So this led us to ask ourselves if UVVR might not be the correct vulnerability indicator for this question. So when you look at this correlation matrix of all the variables, you see that UVVR has very weak correlations with all of them. But another potential indicator of marsh vulnerability, elevation, has a much greater correlation with a lot of the other variables across the board. And we also found, interestingly enough, that UVVR's highest correlation also happened to be with elevation. And so because of this information, we rethought about our data and our model structure, and we rearranged it to use elevation as our dependent variable instead of UVVR. And when we did this, we found that our model fit was greatly improved. And this leads us to think that our model might look a little something like this, where all of our variables are influencing elevation, and elevation is affecting UVVR. And it's also important to note that even under this modified model, that ditches have a very small negative effect on elevation. And this kind of reaffirms what most of us already know, which is that marshes are very complex systems, and they have multiple stressors that are affecting their long-term health. And the fact that ditches seemingly play a smaller role in affecting marsh vulnerability is probably a good thing, since, as we said before, there was a larger length of ditches than the diameter of the Earth in the Northeast. And the prospect of restoring all of those ditches is just a truly daunting task. So where do we go from here? Well, our next task is that we'd really like to find out what the rest of this model looks like and how these other variables are interacting to affect marsh vulnerability. And we also would like to use this information to influence management decisions. So it'd be great to know how all these factors are influencing elevation and marsh vulnerability, and understand the underlying mechanisms. But we would also like to know what changes managers can make to influence these processes. So making it actually useful in making meaningful change for the future of marshes in this region. So one tactic that we are looking into using, and this is very preliminary and very subject to change, so take it with a grain of salt at this point, but we are attempting to use structural equation modeling, which is a mix of path analysis and factor analysis, to model some of these interactions between the variables that we have drawn together. So in this, arrows represent different relationships between variables. And in the context of the study, this model shows that tide range, sea level rise, and elevation load onto a similar latent variable that I represented in blue circle called hydro. And this just means a large amount of their variability is correlated. And we also do see that there is covariation between UVVR, which I have labeled as veg here in the model, and elevation, which is something that we'd already also suspected. And lastly, we do see a very small negative effect of ditches on UVVR, which is also something that we've pulled out before. With that, we also have to show that we do have some limitations with looking at this data, which is that we are modeling with model data, which always means that you're going to have to use quite a bit of asterisks. But we're hoping that this will help us to pull out large-scale trends that can be used to make large-scale management decisions. It's also making generalizations across the entire region. So me and Erin have really talked a lot about scale and had a lot of discussions about scale. And we want to make sure that that's emphasized, that you really want to match your questions to the models that you're using and the scale of the data that we're using. We're also missing parts of the puzzle. So we know that we don't have all of the parts that are influencing marsh vulnerability, and that's going to lead to some gaps. So our ask from you is, do you have some of our missing puzzle pieces? So we are always looking to fill in some of those gaps in our data as we are building our structural equation model to see how vulnerability of marshes are affected by these other factors. We're also looking for more continuous wave data across the entire US, and potentially better accurate suspended sediment data than the model that we are currently using. So if you have any of those data sets and are interested in sharing or contacting us, please do. Lastly, I again want to highlight that this is a very collaborative project, that we are working with a lot of different partners, and me and Erin have had the great opportunity to work with a lot of great people across all these great institutions, and look forward to continuing this project to see more about how we can help advance marsh restoration and protection in this region. So with that, we'll go to questions and bring Erin back in here too, so she can answer any questions you might have.